Okay, everyone. So today we are going to look into a different artificial intelligence driven methodology where there is a big challenge and also not that much utilized. And this is where how we may be able to inject an human expertise into an artificial intelligence models. So there are several different ways of doing this, but we will look into this by giving a tutorial about that specific methodology, and then and this would be further supported using a number of different examples. This is the artificial intelligence method that we have so far looked into. This is very much data driven. So, for example, we have collected data from different sources, turn into data in a numerical format, and feed into an artificial neural networks is a kind of artificial intelligence machine learning methods, and then we decide the outcome. So we predict something. It's a apple or orange or pear or cherry and so on. But this is very much data driven. So it's a numeric value. But how about human expertise? How about if there is a data, but there is also human expertise, how we can merge these two together to get a better outcome? You remember I showed you a missing data or too much data. So human expertise would be able to complement this. It becomes a complementary component of your model development. But this has not been that much explored. So now we have two different forms, two different platforms when you are developing a decision-making tool within the context of artificial intelligence. So the first one is data-driven, as I mentioned, and also if you talk to a human, that person may be able to guide you through to make a better decision. For example, you need to use a tool or machine. There may be an instruction, but that person may have been using that machine for a long time, and you can go and then ask that person different information, and you can get a tacit knowledge from that person's brain and use it in your own life. Why this is important within the context of architectural restoration? The reason is that the data is maybe there, but the historians have the best information about that architecture. And then that person would be able to give you better information about how you may be able to find a way of restoring that historical building to the near real, near perfect form. So that's why this is particularly important in this context. So you go and collect your data and drive the data into your artificial intelligence model, learn it from the data. But there is always a missing data because you may not know historical knowledge. Go and get the historical knowledge from the text or from the historians and come up with this piece of information and feed into the system. And then finally, you can merge these two to have a better decision for different purposes, in particular case, a historical building restoration or any kind of, because even if you are designing a new home or if you are constructing a new living space, you can go and talk to experienced people and get the rules in their head, and then you may be able to make it better and faster. So that's why we want to have an introduction session here along with the tutorial to describe this model, and it may be used in the future applications. So you can find a lot of documents about the data-driven models. Even you don't need to create one. For example, transfer learning, for example, deep learning, and you can just feed the data, and then the transfer learning models that are already available may be able to run for you straight away, because it is becoming more diversified, democratized for everyone. It's like a plug and play. It is like a Microsoft Office, so you just open and use it, but it's getting better. Whereas I think you need to what you need to be aware of here is that how you can use also human expertise and inject into such models to have a better understanding of your algorithms. I think this is particularly important. And in this last course, in this tutorial, I will be giving you the meaning of that methodology. Just be patient, it's not hidden, so I will reveal the name of that methodology, and you will understand what it means, and hopefully this is something that you may be able to use it in the future. This is a low-level course, low-level tutorial, but there are several tools that you may be able to use, and these tools may be able to help you inject these two different models together for future applications. So this is called fuzzy logic. So what I missed here is that this is not only about human expertise, human rules that could be injected into the system, but also using fuzzy logic and fuzzy if-then rules, you will be able to capture the uncertainty that exists in your data set or in your model or in the things that you are trying to model. So if you look at in a normal Boolean logic that was developed several decades ago, and there are two outputs, either 1 or 0. So in your life, either you are short or tall, either you are fat or slim. So, but this is not the case in the normal life. For example, you may live in a country where there's a huge heat, for example, very hot. So you may think that, oh, 40 degrees is not that much hot, but it is subject to what you feel. So in that case, having a hot temperature is subjective, and it depends on the person's living space, living place. So therefore, there is no sharp boundaries between concepts, except for certain things, of course. But I think being a short or tall is still subject to an interpretation. Having hot and cold is still subject to interpretation, and so on. But there needs a kind of a smooth transition from one concept to another concept. So you may be able to assign a degree of belonging to these concepts. So between 1 and 0. So short doesn't have to be 0, tall doesn't have to be 1, but there may be a different degree of belongings in this context. So fuzzy logic is based on fuzzy sets. Fuzzy sets is is like a Boolean set, but the difference is, as I mentioned, is a degree of belonging between 0 and 1. So it is very much defined by it is membership values and membership functions. So membership function is a function that has a value between 0 and 1 that represents degree of belonging. For example, 40 degrees, for example, let's give an example, hot and cold. Put a boundary at 35 degrees. So 34 degrees in the Boolean logic is regarded as 0, 35 or even 36 is regarded as 1 because this is hot. But only 1 degree between them, and because you put a sharp boundary, 1 is 0, 1 is 1. So in that case, this is not the way you should be modeling the system. And it depends on different parameters. Instead of Boolean function 1 and 0, you can put the membership function that defines the degree of belonging. For example, you have two different classes, hot and cold. 35, for example, 34 degrees may belong to a cold group with a degree of 0.8, whereas 35 degrees belongs to a hot weather class with a degree of 7, degree of 6. So therefore, now you have a better understanding of degree of belonging, so there is no sharp boundary. So I think, and I will be coming to that point later, but in order for you to give information, the if-then rules or fuzzy if-then rules are also built upon these fuzzy membership functions and fuzzy sets to model your system. So I think it's worth mentioning at this stage why I was talking about the membership function, why I was talking about fuzzy sets and so on. So let's have a look at a bit of historical perspective. So because fuzzy logic is similar to the way we talk and think, it is easier for us to just adjust. This is one a statement from one of the scientists here. What else we can talk about? So fuzzy logic is particularly good at handling uncertainty and imprecision in this context because we are representing this in different ways with different degree of belongings. There is no sharp boundary, so we are not cutting the things in the middle. And fuzzy logic is especially useful where a problem can be described linguistically, for example, using words, or with neural network where there's a data or you are looking for relationship with or patterns with that data. So what you can see here is that you can describe a model or event, not only data, but also the words. And you can build if-then rules based upon this. And also, fuzzy logic uses imprecision to provide robust, tractable solutions to the problems. And fuzzy logic relies on the concept of a fuzzy set because you have different groups and each group may become a set, but as opposed to the Boolean set, so for example, in the Boolean set, one object belongs to only one group. So belonging degree of that object to that group is 1 and 0 to others. In the fuzzy set, one object belongs to all these different groups with different degrees of membership. So actually it was introduced by Lutfi Asgarzadeh, unfortunately who passed away a few years ago. It was introduced by him in 1965 in his seminal paper published in Fuzzy Sets Information and Control. Okay, let's consider the first example, how you may be able to define tall and short groups. So on the left-hand side, you can see a crisp way of modeling tallness. So you have defined your boundaries. Now, this is 5 feet 11 inches and 7 feet. And then if somebody who is shorter than 5 feet 11 inches, this could be described as a person who's short. So this is the way you can use in the Boolean logic. It's a 1 or 0 logic. How would you be able to expand this to cover different terminology? For example, now in the previous example, we said either tall or short, but how would you be able to expand this by adding more words, more definition, more phrases, quite tall, very tall, short or very short, and so on. So you can see that you can expand this by adding more words. But instead of this, how would you be able to use a different function to represent these sets, quite tall, very tall, and so on? So rather than keep expanding this, for example, yes, we are talking about tall here, but how about quite tall, very tall, very, very tall, and so on? So this modeling or the definition goes and on and on. But is there any way we can represent in a different way? Yes, we can. Instead of this, you may be able to use a membership function to represent it easily. So, for example, a possible fuzzy set for to represent people who are tall. So between 5 feet and 11 inches and 7 feet, and you can see that different degree of membership. So for example, this is tall, this bit is tall, and this bit may be too very tall, and may be getting shorter here. So you can see that you can define it with a degree of membership here, rather than with the terminology. So again, here you can talk about the short, and you can see that this is coming down and with different degrees of membership. Now put these together, and now you have two membership functions that can represent two different concepts, tallness and those who are short. Let's give an example. For example, somebody who has this height, 5 feet 11 inches. You can see that that person belongs to tall group with a degree of membership of 0.40, but the same person still belongs to another group, short group, with a degree of 0.75. So it means that there is no sharp boundary between short and tall, and that person doesn't belong to other group, only belongs to, for example, short group or tall group, but that person has two different belongings, short group and tall group, with a degree or different degrees of membership. You can still make a judgment of to which group that person is likely to belong to if you want to have a crisp decision. So if you want to have a crisp decision, of course, you can take the maximum of that person should belong to short group because of a larger degree of membership. So now we have got away from all these different terminologies. Now we have represent this uncertainty using two membership functions, each one of which represents a different concept. Okay, actually, fuzzy logic has a maths. So let me just go through this a bit with you. For any fuzzy set, let's name it as fuzzy set A, it has a function, and this function mu A represents a membership function. And if you want to find a degree of membership for one particular object in that fuzzy set A, so this is how you indicate it, mu AX. So how would you be able to read it? So X is an object in that fuzzy set A, and mu it is its membership, and its membership is between 1 and 0. So fuzzy sets can be either discrete or continuous, so it depends on the situation. It can be, but if you are going to make a machine learning type of fuzzy set, I will be describing in the future, it needs to be continuous, but in some cases it may be discrete. So there are notations for fuzzy set. So for the member X or discrete set with membership mu, so we use notation X in that way. This is a discrete fuzzy set, as so it means that I have in the discrete fuzzy sets, I have fuzzy set A, and it has objects inside that A, x1, x2, xn, and then each one of which has a degree of membership. For example, for x1, it has a membership degree of mu1. xn, it has a membership degree of mu n. So, but in more compact form, it is defined as it is. So when we say fuzzy set, so for example, it may be humans with different ages or different heights and so on. So, and a continuous fuzzy set with continuous membership function is defined as like this, and it's described as a function. For example, this is a Gaussian membership function, and each number has its own degree of membership here. You can turn continuous function into discrete membership function by taking some samples in the x-axis. So if you look at a different part, for example, a different example, young, middle-aged, and old, you are trying to model these. Age is subject to a certain interpretation. For example, somebody who's at the age of 30 is maybe young, maybe middle-aged, even in some countries maybe old, because of the lifetime expectancy. So in that case, this needs to be modeled by using membership function, and we need to look at different degree of membership for person who has at certain age. So, and now what we have been using here is a linguistic term to be able to model it as well. So let's have a look at the key points for fuzzy set. So the members of a fuzzy set are members to some degree, known as a membership grade or degree of membership. So you have a set, in this context a fuzzy set, because every member of the fuzzy set belongs to all these sets with different degrees of membership. And fuzzy set is fully determined by the membership function. There are so many different membership functions that you can use. Now we have already seen some, I'm not quite sure if you remember, triangle, trapezoidal, Gaussian, and so on. Membership grade is the degree of belonging to fuzzy set. The larger the member, the larger number A, and the more the degree of belonging. So basically, 1 means that person or that object belongs to that group only, the others 0. Translation from X to mu AX is known as fuzzification. So fuzzification is particularly an important component of that system. So, for example, you have an age of 50, but if you use degree of membership of that age, is called classification. So an object is defined or determined by a degree of membership. This process is called classification. So as we mentioned, fuzzy set is either continuous or discrete. In case of discrete, you use discrete membership function. Continuous, this is where you can use the continuous membership function. Although there's a debate, fuzzy sets are not probabilities. Graphical representation of a membership function is very useful because you have already seen in different ways. So membership functions is the core component of fuzzy logic fuzzy sets. So one of the key issues in all fuzzy sets is how to determine fuzzy membership function. And also membership functions fully define the fuzzy set. A membership function provides a measure of the degree of similarity of an element to a fuzzy set. Membership functions can take any form, but there are some common examples that appear in real applications. Without a fuzzy membership function, you wouldn't be able to do the fuzzification, and you wouldn't be able to define it or determine degree of belonging to a group for a particular object. And in some cases, you may not be able to do a continuous calculation if you are going to develop a learning, self-learning system based on fuzzy if-then rules. So membership functions either be chosen by the user arbitrarily based on user experience, and membership function chosen by two different experts or users could be different depending on their experience, perspective, and so on, or could be designed using machine learning methods, using artificial neural networks, genetic algorithms, or similar architecture. So there are common forms of membership functions, and these are the most common ones: triangular, trapezoidal, piecewise linear, Gaussian, bell-shaped, and very similar ones. So depending on your application domain, so you may pick up different ones. But what is interesting here is that we also said we use machine learning methods to be able to develop and drive membership functions here as well. So this is where you can see a data-driven model is being used to develop a fuzzy if-then rules, and it is components as well. So so that's why this is particularly important subject domain. So let's have a look at different membership functions here. So this is a triangular membership function. It has four main components. The first one is actually there are also three main parameters that define the membership function. So the value A determines the lower boundary, C determines the upper boundary, and B determines where the degree of membership is 1. Other than this, degree of membership is going to be 0 if it is less than A and higher than C, and if it is between A and B, if it's A and B, A and C, sorry, it takes this degree, it's calculated in this way. So this is very much commonly used, and it's very useful in certain aspects, and it is also learnable. If you use artificial neural networks, you can easily learn A and B and C and fit into the data. So another membership function is Gaussian membership function. It is determined by 3 parameters. So one is the middle point, the center, this is where degree of membership is always 1, and symmetrically the other values define or determine degree of membership for each member of that group. So x-axis here. And another parameter is s, is width, that determines how sharp or wide that figure is. And another one is m, is also another parameter that makes this figure sharper or wider. And if you put into the infinite, then you will be able to get a crisp membership function. Let's change the values here, and you will be able to see how this figure, the degree of the membership function changes. So, for example, if you have a smaller value of the width, you can see the sharper one. If it is getting closer to 0, and you will be able to see a very sharp line here, and it's like a Boolean logic. So at 5, it is 1. If it is less than 5 and higher than 5, you may get 0. Again, if it is wider, the width value is higher, so this is getting wider and wider. And then if you get a larger s, so you will get a straight line here. So every value of the set is 1. Okay, let's change the power here. So the smaller power makes it very sharp, and higher value of this value, the power, makes it a bit triangle. So if you have a very large m value, the power here, you may be able to see a sharp rectangle here. So it means that in some cases, you may do it manually, just keep changing to see if this fits into your data. But I'll show you in the future, and this could also be learned using machine learning methods. So you don't have to do it manually. I think this is the main concept behind fuzzy logic and fuzzy sets, and you have also seen the membership functions. I think we will start talking about how you can construct a fuzzy logic to make a decision with different fuzzy logic methods that we have discovered from the real application from the literature. So we will continue discussing this and giving you further information along with some examples.